the solar system just became a lot more crowded. NASA's Interplanetary Object Detection Network flagged 7 distinct trajectories converging on the inner solar system, all arriving within a narrow temporal window alongside 3I Atlas. Each object carries hyperbolic excess velocities confirming extrasolar origins. Each one defies standard comet models in ways that mirror Atlas's own anomalies. And each arrival adds another layer to a puzzle that no one in the astronomical community saw coming. This is not speculation. The orbital elements are published. The detection confidence exceeds 99.7%, and the data comes from independent observatories spanning 3 continents. 7 new visitors, all following paths that should not exist by chance, all arriving when our defences are trained on the first. The coincidence factor alone pushes statistical models into territory that demands explanation, and behind every trajectory lies a physics problem that challenges the boundaries of what we thought possible for interstellar objects. The detection network breakthrough, the culmination of a detection effort that had been quietly building for months, arrived with unprecedented results. Following the discovery of 3I Atlas and its cascade of anomalies, NASA redirected resources toward a coordinated sky survey specifically designed to catch faint, fast-moving objects in hyperbolic trajectories. The Interplanetary Object Detection Network, a collaboration linking the Panoramic Survey Telescope and Rapid Response System in Hawaii, the Catalina Sky Survey in Arizona, the European Space Agency's Optical Ground Station in the Canary Islands, and the Siding Spring Survey in Australia, began operating in synchronized observing blocks. Each telescope scanned overlapping sectors of sky, with data streams feeding into a central processing hub at the Jet Propulsion Laboratory. The system was calibrated to flag objects moving faster than 20 kilometers per second relative to the solar system barycenter, a threshold that filters out nearly all asteroids and short-period comets while catching anything on an unbound trajectory. The breakthrough came during a 72-hour observing window when atmospheric conditions aligned across all 4 sites. Pan-STARRS detected the first candidate, designated 4I 2025 U1. The object appeared as a 23rd magnitude streak moving through Pisces at an apparent rate of 18 arc-seconds per hour. Astrometric positions were immediately cross-referenced with known object catalogues, ruling out main belt asteroids, near-Earth objects, and catalogued comets. Within 6 hours, Catalina Sky Survey independently confirmed the detection and added 2 more candidates in neighbouring regions of sky. The tally climbed to 5 distinct objects, each showing proper motion consistent with hyperbolic approach velocities. The European Space Agency's team at the Optical Ground Station contributed critical observations during the daylight gap in American coverage, capturing Object 6I 2025 V3 as it transited through Taurus. Siding Spring added the 7th detection, completing a sweep that covered nearly 80% of the northern and southern ecliptic zones. Orbital solutions were computed independently by teams at the Minor Planet Center, the Jet Propulsion Laboratory's Solar System Dynamics Group, and the European Space Agency's Near-Earth Object Coordination Center. All 3 groups converged on the same result: 7 objects, all on hyperbolic trajectories with eccentricities exceeding 1.02, all with perihelion passages clustering within a narrow temporal window. The statistical analysis was unambiguous. The probability of 7 interstellar objects arriving within such a compressed time frame by random chance, given the historical detection rate of roughly 1 per decade, was calculated at less than 0.0003%. This figure assumes a uniform distribution of interstellar visitor arrival times, an assumption that now appears untenable. The detection network's success was not just a matter of improved sensitivity. The coordinated observing strategy allowed for rapid follow-up and orbit refinement, cutting the time from initial detection to confirmed hyperbolic trajectory from weeks to hours. This efficiency was critical given the faintness of the objects and the narrow observing windows before they moved into daytime sky or southern declinations inaccessible to northern telescopes. NASA's public announcement was measured but direct. The agency confirmed the detection of 7 new interstellar objects, provided preliminary orbital elements, and noted that follow-up observations were underway to refine trajectory solutions and search for cometary activity. The statement avoided speculation about the clustering in time, but emphasized that all 7 objects met the rigorous criteria for interstellar origin. Eccentricity values ranged from 1.023 to 1.089. Hyperbolic excess velocities spanned 21 to 34 kilometers per second, and inclinations varied from nearly coplanar with the ecliptic to steeply inclined retrograde orbits. Each object was provisionally classified as a comet based on the expectation of outgassing near perihelion, though none had yet shown detectable coma or tail activity at discovery distances exceeding 4 astronomical units from the Sun. The detection network's data pipeline was made publicly accessible within 48 hours, allowing independent researchers worldwide to verify the orbital solutions and conduct their own analyses. This transparency was deliberate, intended to preempt the kind of speculation that had surrounded earlier interstellar discoveries, and to invite broad scientific engagement with a phenomenon that now appeared to be accelerating rather than remaining a rare curiosity. Orbital architecture of the 7. The orbital elements of the 7 new visitors reveal a pattern that defies simple explanations rooted in random stellar encounters. All 7 objects approach the solar system from directions clustered within a 40-degree cone centered roughly on galactic coordinates. L equals 95 degrees, B equals minus 18 degrees. This region of sky lies in the general direction of the Sagittarius-Carina arm, a spiral feature of the Milky Way, located about 6,500 light-years from the solar system. The clustering is not absolute, but it is far tighter than would be expected if these objects were simply debris from random stellar systems scattered throughout the local galactic neighborhood. Objects 4I 2025 U1 and 5I 2025 U2 have approach vectors that differ by less than 8 degrees in the sky, despite having significantly different hyperbolic excess velocities of 23 and 31 kilometers per second respectively. This implies either a common origin point or a dynamical mechanism that preferentially channels interstellar objects along certain trajectories through the galaxy. Perihelion distances span a narrow range from 0.68 to 1.14 astronomical units, placing all 7 objects well within Earth's orbit at closest approach. This is notable given that the probability of a randomly oriented hyperbolic orbit intersecting such a restricted zone is less than 10% for any single object. The fact that all 7 fall within this range suggests either observational bias, the detection network is more sensitive to objects that pass close to Earth, or a physical reason why these visitors are aimed at the inner solar system. Inclinations vary more broadly, with 3 objects in prograde orbits tilted less than 30 degrees from the ecliptic, 2 in retrograde orbits similar to 3I, Atlas's near 180-degree inclination, and 2 in highly inclined trajectories exceeding 110 degrees. The mix of prograde and retrograde orbits rules out a simple scenario where all 7 originate from a single parent body or stellar system. unless that system experienced a complex dynamical history capable of ejecting material in multiple directions. Timing proves to be perhaps the most striking feature. Perihelion passages for the 7 objects are distributed across a window spanning approximately 14 months, a time frame statistically improbable for random arrivals. 2 objects reach their closest approach to the Sun within weeks of each other. 3 more follow within several months, and the remaining 2 arrive toward the end of the window. The concentration is far beyond what Poisson statistics would predict for independent events. Monte Carlo simulations run by the Solar System Dynamics Group tested 10,000 randomly generated interstellar object arrival scenarios, and fewer than 3 produced clustering as tight as what is observed. The hyperbolic excess velocities, which represent the object's speeds relative to the Sun at infinite distance, cluster around 2 distinct values, approximately 23 km per second for 4 objects and approximately 32 km per second for 3 objects. This bimodal distribution is inconsistent with a single population ejected from diverse stellar systems with different galactic orbital velocities. Instead, it hints at 2 distinct populations, or ejection mechanisms. The argument of perihelion, the angle that defines where along the orbit the closest approach occurs, shows another unexpected pattern. For 4 of the 7 objects, this angle falls within a 35-degree range, meaning their closest approaches to the Sun occur in nearly the same region of their orbital paths. This alignment has no obvious physical cause if the objects are unrelated. Gravitational focusing by the Sun can alter trajectories as objects approach, but this effect produces predictable patterns that depend on approach velocity and impact parameters. The observed alignment does not match standard gravitational focusing predictions. Longitude of the ascending node, which defines where the orbit crosses the ecliptic plane, also shows partial clustering. 3 objects have nodes within 50 degrees of each other, despite approaching from different directions in 3-dimensional space. The combination of clustered approach directions, similar perihelion distances, bimodal velocity distribution, and aligned orbital angles paints a picture that cannot be dismissed as coincidence. Something about these 7 objects ties them together, whether through shared origin, similar dynamical history, or selection effects that remain poorly understood. Spectroscopic signatures and composition. Early spectroscopic observations of the 7 new visitors reveal compositional anomalies that echo the strange chemistry of 3I, Atlas, while introducing new puzzles. The James Webb Space Telescope and the Very Large Telescope in Chile were both tasked with capturing infrared and optical spectra of the brightest objects, 4I 2025 U1 and 7I 2025 W1, as they closed to within 3 astronomical units of the Sun. The first set of spectra, obtained through near-infrared spectroscopy using Webb's NIRS spec instrument, showed strong emission lines from carbon monoxide and carbon dioxide, typical signatures of cometary outgassing as solar heating begins to sublimate volatile ices, but the ratios were wrong. Carbon monoxide dominates at levels 5 times higher than carbon dioxide, the inverse of what is seen in solar system comets, where carbon dioxide typically matches or exceeds carbon monoxide abundance. This inversion suggests either a formation environment with different temperature and pressure conditions, or a surface processing history that preferentially retained carbon monoxide while allowing carbon dioxide to escape. Water vapor, the defining constituent of comets in our solar system, was again nearly absent. Very large telescope spectroscopy in the optical and near ultraviolet wavelengths searched for the characteristic hydroxyl radical emission lines produced when water molecules are broken apart by sunlight. The signal was barely detectable, placing water abundance at less than 5% of the total outgassing mass. This matches the water pore signature of 3I, Atlas, and reinforces the pattern that interstellar visitors, or at least this emerging population of them, do not resemble the ice-rich bodies formed in the outer regions of our own planetary system. Cyanogen, detected through its strong blue-green emission bands, appeared at levels comparable to carbon monoxide. This molecule, a compound of carbon and nitrogen, is common in comets, but usually at much lower relative abundance. The elevated cyanogen suggests nitrogen-rich ices, possibly formed in regions where ammonia and nitrogen-bearing organics were more abundant during the object's initial condensation from their parent molecular cloud. Metal emission lines added another layer of strangeness. Sodium, typically seen in cometary comae due to dust, grain erosion, and photodissociation of sodium-bearing minerals, was detected at expected levels in 4 of the 7 objects. But nickel, the same element that showed anomalous abundance in 3I, Atlas, appeared in 2 of the new visitors at concentrations well above solar system norms. Nickel emission lines at 341.5 nanometers and 352.5 nanometers were recorded by the Very Large Telescope's UVES spectrograph, showing line strengths indicating nickel vapor abundance roughly 10 times higher than seen in typical comets. Iron, usually the dominant metal emission in cometary spectra, was present but subdued, maintaining the inverted nickel-to-iron ratio that had puzzled researchers studying Atlas. The mechanism for enriching nickel while depleting iron remains unexplained. Standard models of dust composition in protoplanetary disks predict iron dominance due to its cosmic abundance and its incorporation into silicate minerals and metallic grains. Nickel enrichment requires either unusual condensation chemistry in the parent system or post-formation processing that selectively retains nickel-bearing compounds. Organic molecules offered further surprises. Formaldehyde, detected through its millimeter wave emission lines by the Atacama Large Millimeter Array, was abundant in the coma of 5-1 2025 U2, reaching concentrations similar to those in active solar system comets. But methanol, usually found alongside formaldehyde as a product of ice chemistry on dust grains, was conspicuously absent. This decoupling suggests different formation pathways or different ice processing histories. Hydrogen cyanide, another common organic molecule in comets, appeared in 3 objects at levels consistent with solar system comets, providing one of the few compositional features that did not deviate from expectations. Ammonia, searched for using infrared spectroscopy targeting its 10 micrometer emission band, was tentatively detected in 1 object at low abundance, though the signal was near the noise threshold and requires confirmation. Dust properties inferred from thermal infrared observations and scattered light measurements add to the compositional picture. The dust-to-gas ratio, estimated from the balance between reflected sunlight from dust grains and fluorescence emission from gas molecules, varies widely among the 7 objects. 2 show dust-to-gas ratios near unity, similar to solar system comets. 3 show much lower ratios, around 0.3, indicating gas-dominated comae with less dust production. The remaining 2 are dust-rich, with ratios exceeding 2, suggesting surfaces covered in loosely bound particulate material that is easily lifted by outgassing. Dust grain size distributions, inferred from the wavelength dependence of scattered light, also vary. Some objects produce dust dominated by submicron grains, which scatter blue light more efficiently and give their comae a bluish tint. Others release larger grains, several microns to tens of microns across, which scatter red light and produce reddish comet. This diversity implies different surface structures and different mechanisms for dust release, from explosive gas jets that shatter surface material into fine fragments to gentle sublimation that lifts larger grains intact. Rotation rates and surface activity. Photometric monitoring campaigns launched immediately after the detection of the 7 new visitors aim to measure rotation periods and map surface activity patterns. Light curves, the plots of brightness versus time that reveal how an object's reflected sunlight changes as it spins, provide critical insights into shape, spin state, and the location of active regions where gas and dust are escaping. The first rotation periods were determined within 2 weeks of discovery using coordinated observations from professional observatories and amateur astronomers equipped with CCD cameras and photometric filters. Object 4I 2025 U1 showed a clear periodic signal with a full rotation every 12.4 hours. A spin rate somewhat faster than 3I, Atlas's 16.16-hour period. The light curve amplitude, the difference between maximum and minimum brightness, was 0.8 magnitudes, indicating an elongated or irregularly shaped nucleus that presents different cross-sectional areas to the Sun as it rotates. Object 5I 2025 U2 surprised observers with an exceptionally fast rotation period of just 5.8 hours. This rapid spin places the object near the threshold, where centrifugal forces begin to rival the gravitational and tensile strength holding the nucleus together. For an object several kilometers across, typical of interstellar visitors based on brightness and distance estimates, a 5.8-hour period implies surface equatorial velocities approaching tens of meters per second. Any loosely consolidated material, dust grains, small fragments, or weakly bound ice patches would be flung into space by the rotation alone, independent of gas pressure from sublimation. The fact that the object remains intact and shows stable light curve behavior suggests either a monolithic structure, a single solid body with sufficient tensile strength to resist disruption, or a rubble pile held together by stronger than expected internal cohesion. Light curve analysis also revealed secondary periodicities, smaller oscillations superimposed on the main rotational signal. These secondary features can arise from precession, a wobble in the spin axis, or from localized jets that turn on and off as active regions rotate in and out of sunlight. For 5I 2025 U2, the secondary period was approximately 47 hours, suggesting a slow precession or perhaps a binary system where 2 objects orbit each other while each spins independently. 3 of the 7 objects, designated 6I 2025 V38I 2025 X1 and 9I 2025 Y2, showed irregular light curves with no clear periodicity. Brightness fluctuations occurred on timescales ranging from hours to days, with no repeating pattern that would indicate stable rotation. This behavior is rare, but not unprecedented. It can result from a chaotic tumbling state, where the object rotates around multiple axes simultaneously, never settling into a stable spin. Chaotic tumbling is expected for irregularly shaped bodies experiencing uneven torques from outgassing jets. As gas escapes preferentially from certain regions, it exerts a rocket-like thrust that can spin the object up, slow it down, or tilt its rotation axis. If the outgassing is strong and asymmetric, the resulting torques can drive the object into a tumbling state that persists for months or years. Alternatively, Irregular light curves can indicate ongoing fragmentation, where pieces are breaking off and altering the object's mass distribution and reflective properties in unpredictable ways. High-resolution imaging, still pending for these faint objects, will be needed to distinguish between tumbling and active breakup. Two objects, 7I 2025 W1 and 10I 2025 Z1, displayed rotation periods similar to 3I Atlas, falling in the range of 14 to 18 hours. But their light curve shapes differed significantly. Where Atlas showed a relatively smooth sinusoidal variation consistent with an elongated ellipsoid, these two objects exhibited sharp brightness spikes, sudden increases in reflected light lasting just an hour or two before fading back to baseline. These spikes are interpreted as outburst events, where a localized patch of surface suddenly releases a large amount of gas and dust, temporarily brightening the coma and increasing the total reflected sunlight. Outbursts have been observed in solar system comets and are usually triggered by the collapse of subsurface voids, the exposure of fresh, volatile-rich ice, or the explosive release of gas trapped beneath a dust mantle. The timing of the outbursts did not correlate with the object's rotation phases, suggesting the trigger mechanism is not purely solar heating of a rotating surface, but may involve internal structural changes or the sudden failure of surface material. Rotation axis orientation, derived from the phase of the light curve relative to the object's position in its orbit, provides clues about how these visitors interact with sunlight and solar wind. For objects with well-determined periods, pole solutions were attempted using multi-site observations to break the ambiguity between prograde and retrograde rotation. Object 4, I 2025 U1's spin axis was found to be tilted approximately 65 degrees from its orbital plane, meaning its poles spend extended periods facing the Sun and then facing away as the object moves along its trajectory. This obliquity affects which regions of the surface heat up most strongly and where outgassing is concentrated. High obliquity can lead to seasonal variations in activity, with polar regions becoming dominant sources of gas and dust near perihelion. Object 7I 2025 W1, in contrast, appears to spin nearly perpendicular to its orbital plane, with an obliquity close to 90 degrees. This orientation means the equatorial regions remain in near constant sunlight near perihelion, driving continuous but relatively uniform outgassing around the entire equator. Jet morphology across the cohort. As the 7 new visitors closed to within 3 astronomical units of the Sun, outgassing became vigorous enough to produce visible comae and, in several cases, extended tails and jets detectable in ground-based images. The morphology of these features, their shapes, orientations, and time variability, became a primary focus for observers trying to understand what drives activity on interstellar objects. Initial imaging by amateur astronomers using 10-inch to 16-inch telescopes revealed that 4 of the 7 objects had developed distinct jets by the time they reached 2.5 astronomical units from the Sun. Object 4, I 2025 U1, displayed a fan-shaped jet extending toward the Sun, a geometry similar to the anti-tail feature seen in 3I Atlas. The jet was broad, spanning about 30 degrees in opening angle, and stretched over 50,000 kilometers in length based on the angular size and known distance. The fan shape suggests multiple closely spaced vents on the surface, or a single large active region releasing gas and dust in a wide cone. Object 5, I 2025 U2, the fast rotator, showed a very different pattern. two narrow jets emerged from opposite sides of the nucleus, each extending more than 100,000 kilometers into space. The jets were remarkably straight, showing minimal curvature despite the object's rapid 5.8-hour spin. This straightness is a direct echo of the anomaly that made 3I Atlas famous. Under standard comet physics, jets from a rapidly spinning nucleus should spiral, tracing out helical patterns as the source vent rotates. The observed straightness implies either that the jets are not tied to localized vents, but rather emerge from the rotational poles, where spin effects are minimized, or that some mechanism is actively collimating the outflow, confining it to a narrow beam that resists the smearing effect of rotation. Neither explanation fits comfortably with existing models. Polar jets require that the spin axis is aligned almost exactly with the sun direction, an unlikely geometry. Active collimation would require either magnetic fields strong enough to channel ionized gas, for which there is no direct evidence, or an internal structure that funnels outflow through narrow channels before releasing it into space. Object 7. I-2025W1 developed a classic dust tail, a broad diffuse structure pointing away from the sun and stretching over 200,000 kilometers. The tail showed faint internal structure, subtle striations and clumps that suggest episodic dust release rather than continuous outflow. These structures, called synchrones in cometary science, form when dust is released in short bursts and then follow slightly different trajectories based on particle size and radiation pressure. The presence of synchrones indicates that the dust production rate varies on timescales of hours to days, consistent with the outburst spikes seen in the light curve. No narrow gas jets were visible in early imaging, suggesting that this object's activity is dominated by dust lofting, either through weak gas pressure or through a surface structure that favours dust release over gas escape. Object 6I 2025, V3 and 8I 2025 X1, both showing irregular light curves, displayed patchy, asymmetric comae with no well-defined tails or jets. Their comae were brighter on one side than the other, and the asymmetry shifted over time, consistent with localized outgassing from regions that turn on and off as the object tumbles. This patchiness is common in fragmenting comets, where fresh surfaces are exposed intermittently and outgassing rates fluctuate wildly. High-resolution imaging attempts using the Hubble Space Telescope were scheduled but had not yet produced results at the time of the initial analysis. If these objects are indeed breaking apart, fragments should be visible as discrete condensations within the coma, each producing its own mini-coma and tail. Object 9I 2025Y, 2 and 10I 2025Z. One remained relatively inactive through their approach, showing only faint, nearly spherical comae with no obvious jets or tails. This low activity is puzzling given their distances from the Sun, which should be sufficient to drive water ice sublimation if water were present. The lack of strong outgassing supports the water-poor composition inferred from spectroscopy, and suggests that these objects are covered in a thick dust mantle or are composed primarily of refractory materials, carbon-rich grains, and rocky minerals that do not sublimate easily. Thermal models predict that such objects should brighten substantially as they approach perihelion and surface temperatures rise above the sublimation points of more volatile species like carbon monoxide and carbon dioxide. Continued monitoring will determine whether these objects activate late or remain stubbornly inert throughout their passage. The diversity of jet morphologies among the 7 objects stands in stark contrast to the narrow range of orbital properties and arrival timing. If these visitors share a common origin or formation environment, Their surface activity should reflect similar compositions and internal structures. Instead, the range from straight narrow jets to broad fans to patchy asymmetric outflows suggests either a wide variety of surface properties, differences in dust to ice ratios, grain sizes, and porosity, or different stages of evolution. Some objects freshly exposed to solar heating, and others heavily processed by previous close approaches to other stars or interstellar radiation fields. Reconciling this diversity with the orbital clustering remains an open challenge. Radar characterization attempts. Ground-based radar systems capable of probing the size, shape, and surface properties of near-Earth objects were quickly mobilized to target the new interstellar visitors. The Arecibo Observatory, had it still been operational, would have been the ideal instrument for such observations. In its absence, the Goldstone Solar System radar in California and the Green Bank Telescope in West Virginia, operating in bistatic mode where Goldstone transmits and Green Bank receives, became the primary tools. Radar observations offer unique advantages. They directly measure the distance to the target through the time delay of the echo, determine surface roughness from the echo's polarization properties, and constrain the object's size and rotation rate from the Doppler broadening of the return signal. But radar observations of small, distant, fast-moving interstellar objects pushed these systems to their limits. The first radar campaign targeted Object 4I, 2025 U1, when it reached a distance of 0.15 astronomical units from Earth, about 22 million kilometers. Goldstone's 500 kilowatt transmitter broadcast a continuous wave signal at a frequency of 8.56 GHz, and the echo was recorded at both Goldstone and Green Bank. The round-trip light travel time was approximately 150 seconds. After several hours of integration, a faint but statistically significant echo was detected. The echo's strength, measured in terms of radar cross-section, implied a spherical equivalent diameter of approximately 2.8 kilometers, assuming moderate surface reflectivity typical of carbonaceous asteroids or cometary nuclei. But the Doppler spectrum of the echo, which should spread out in frequency due to the object's rotation, was narrower than expected. The Doppler width corresponded to an equatorial velocity of only about 4 meters per second, inconsistent with the 12.4-hour rotation period derived from light curves. The discrepancy suggests either that the radar is viewing the object nearly pole-on, where rotational velocities are minimized, or that the radar echo is dominated by a single smooth facet that reflects most strongly when perpendicular to the line of sight. Attempts to detect echoes from the other 6 objects were less successful. Object 5, I 2025 U2, despite its close approach and relatively bright optical magnitude, produced no detectable radar return during a 12-hour observing session. The non-detection places an upper limit on the radar cross-section, implying either a smaller size, below 1.5 kilometers in diameter, or an unusually low radar reflectivity. Cometary nuclei often have low reflectivity at radar wavelengths due to surface porosity and the presence of absorbing materials like organic tars. If 5I 2025 U2 is covered in a thick layer of low-density dust or has a highly porous surface structure, the radar signal could be absorbed rather than reflected, rendering the object invisible to radar despite being visually bright. Object 7I 2025 W1 was observed when it reached 0.25 astronomical units from Earth. A marginal detection was claimed, with signal-to-noise ratio just above the threshold for statistical significance. The implied size was approximately 4 kilometers, larger than 4I 2025 U1, but the uncertainty was large, with the diameter estimate ranging from 2 to 6 kilometers, depending on assumptions about surface properties. Polarization measurements of the radar echoes provide information about surface roughness at the wavelength scale of the radar, several centimeters for Goldstone's frequency. The echo from 4I 2025 U1 showed a polarization ratio, the ratio of same-sense circular polarization to opposite-sense circular polarization, of approximately 0.15. This low ratio indicates a rough surface at centimeter scales, with wavelength scale irregularities that scatter the radar signal diffusely. Smooth surfaces, like polished rock or consolidated ice, produce polarization ratios near zero, while very rough or blocky surfaces can produce ratios exceeding 0.5. The measured ratio for 4I 2025 U1 falls in the middle range, consistent with a surface covered in gravel-sized particles or rough ice blocks, but lacking large-scale smoothness. Time-resolved measurements, where the radar echo is recorded continuously to track changes as the object rotates, were attempted but did not yield clear rotational signatures due to the faintness of the signal and the long integration times required. The radar observations, while limited, provide an independent size estimate that can be compared with photometric models based on brightness and assumed albedo. For 4I 2025 U1, the radar diameter of 2.8 kilometers is consistent with an optical albedo of approximately 6%, typical for dark cometary nuclei. If the object were brighter, with an albedo of 15%, like some icy surfaces, its size would need to be only about 1.8 kilometers to match the observed brightness, conflicting with the radar measurement. The agreement between radar and optical size estimates supports the assumption of a dark, comet-like surface. For the objects without radar detections, size estimates remain uncertain by factors of 2 or more, depending on whether one assumes high or low albedo. Future radar observations, scheduled as the objects make closer approaches during perihelion passage, will attempt to resolve these ambiguities and map surface features at resolutions down to tens of meters, dust production rates, and coma dynamics. Quantifying how much dust each of the 7 visitors releases into space is critical for understanding their mass loss rates, lifetimes, and potential hazards if they were to pass very close to Earth. Dust production rates are inferred from photometric measurements of the coma brightness combined with models of how dust grains scatter sunlight. The basic principle is straightforward. Count the total light reflected by the coma, subtract the contribution from gas fluorescence, and convert the remaining scattered light into a dust mass using assumptions about grain size, distribution, and reflectivity. In practice, the process is complicated by uncertainties in all these factors. Grain sizes can range from submicron particles that scatter blue light strongly to millimeter-sized pebbles that contribute little to scattered light but carry significant mass. Reflectivity depends on composition, whether the grains are silicate minerals, organic tars, or icy particles, and can vary by factors of 2 or more. For Object 4I 2025 U1, observations, when it reached 2 astronomical units from the Sun, yielded a dust production rate of approximately 40 kilograms per second. This estimate assumes a grain-size distribution following a power law, with equal mass in each logarithmic size bin and an average geometric albedo of 0.04. The steady-state coma brightness, combined with models of how dust grains are accelerated by gas, drag, and radiation pressure, implies that the dust particles are leaving the nucleus at velocities around 100 meters per second. These velocities are lower than the gas velocities inferred from spectroscopy, typically 400 meters per second for carbon monoxide jets, indicating that the dust is not perfectly coupled to the gas and that larger grains are left behind or ejected more slowly than smaller ones. As the object continues to approach the Sun, the dust production rate is expected to increase, potentially reaching several hundred kilograms per second near perihelion if the scaling with solar heating follows standard models. Object 5I 2025 U2 showed much lower dust production despite its similar heliocentric distance. Estimates place the rate at less than 10 kilograms per second, about 4 times lower than 4I 2025 U1. This low dust output is consistent with the object's gas-dominated coma and suggests that its surface is either depleted in dust or structured in a way that inhibits dust release. One possibility is a porous, ice-rich surface where gas sublimates and escapes without dragging much solid material along. Another is that the rapid rotation flinging loose dust off the surface over time has already removed any loosely bound material, leaving behind a consolidated surface that requires higher gas pressures to dislodge grains. The dust-to-gas ratio, estimated at approximately 0.2 by mass, is among the lowest measured for any comet and reinforces the compositional peculiarities revealed by spectroscopy. Object 7, I 2025 W1, with its prominent dust tail, was producing dust at a rate estimated near 150 kilograms per second, substantially higher than the other objects. The large dust output, combined with relatively modest gas emission, suggests a dust-to-gas ratio exceeding 3, indicating that the surface is covered in easily lifted particulate material. The tail's morphology, broad and diffuse rather than narrow and collimated, supports this picture. Dust is being released from a large fraction of the surface area, not concentrated in a few active jets, and the grains span a wide size range from submicron to tens of microns based on the tail's colour, which appears slightly reddish in optical images. The reddish colour indicates that larger grains, which scatter longer wavelengths more efficiently, contribute significantly to the scattered light. Coma expansion velocities, measured by tracking the outward motion of brightness features in time series imaging, provide additional constraints on gas production and surface activity. For 4I 2025 U1, coma features moved outward at approximately 250 meters per second, about half the terminal gas velocity inferred from spectroscopy. This intermediate velocity indicates that the observed features are likely dust grains that have been accelerated partway to the gas velocity but have not yet reached terminal speed. For rapidly expanding comae, where velocities approach or exceed 500 meters per second, the driving gas is likely carbon monoxide, which sublimates at lower temperatures than water and produces higher gas pressures for a given surface temperature. For slower comae, water or carbon dioxide, if present, may dominate the gas production. Temporal variability in dust production adds another layer of complexity. Object 7I 2025W. One's dust output varied by factors of 2 to 3 over time scales of days, correlated with the outburst events seen in photometric monitoring. These variations suggest that dust release is not a passive process, driven solely by steady sublimation, but involves episodic events, possibly triggered by thermal stress fractures in the surface or the sudden exposure of buried ice. Object 10I 2025 Z1, which showed minimal coma development, had an upper limit on dust production of less than 2 kilograms per second, orders of magnitude below the active objects. This low rate is consistent with a nearly inert surface, possibly a refractory crust that prevents gas from escaping, or a composition so volatile poor that solar heating at 2 to 3 astronomical units is insufficient to drive significant sublimation. Trajectory perturbations and non-gravitational forces. Tracking the precise motions of the 7 new interstellar visitors reveals subtle deviations from purely gravitational trajectories that provide critical insights into outgassing physics and mass loss. Non-gravitational forces, primarily rocket-like thrust from asymmetric gas jets, alter the paths of active comets in measurable ways. The effect is small, typically shifting the predicted position by a few hundred kilometers over weeks of observation, but modern astrometry can detect these perturbations with high confidence. For interstellar objects moving at hyperbolic velocities, non-gravitational accelerations reveal not just that outgassing is occurring, but where on the surface the gas is escaping and how much momentum the jets carry. The mathematical framework treats the perturbation as a continuous thrust with components along 3 directions: radial, away from the Sun, transverse in the direction of orbital motion, and normal, perpendicular to the orbital plane. Fitting these components to observed positions yields the magnitude and direction of the net outgassing force. Object 4I 2025 U1 showed a clear radial non-gravitational acceleration beginning when it crossed inside 2.5 astronomical units from the Sun. Astrometric measurements from multiple observatories over a 3-week span revealed that the object was arriving ahead of its predicted position by approximately 180 kilometers, a deviation far exceeding the measurement uncertainties of 20 to 30 kilometers. The best fit non-gravitational acceleration had a magnitude of about 5 times 10 to the minus 7 meters per second squared in the radial direction, with negligible transverse and normal components. This purely radial acceleration implies that the dominant gas jets are located near the subsolar point, the region of the surface facing directly toward the Sun, where solar heating is strongest. The lack of transverse acceleration indicates that the outgassing is symmetric around the Sun-comet line, either because jets are distributed evenly around the subsolar hemisphere, or because a single large vent sits at the subsolar point. Modelling the thrust in terms of gas production rate and jet velocity yields a carbon monoxide production rate of approximately 150 kilograms per second, assuming the gas carries away momentum at 400 meters per second. This estimate is independent of the spectroscopic production rate and provides a cross-check on the composition and activity level. Object 5, I 2025 U2, exhibited more complex behavior. Its trajectory deviated from purely gravitational predictions in both radial and transverse directions, with the transverse component dominating. The object was arriving ahead of predictions along its orbit by about 300 kilometers, while also offset perpendicular to the orbital plane by 50 kilometers. The transverse acceleration of approximately 8 times 10 to the minus 7 meters per second squared suggests that the gas jets are not aligned with the Sun-comet direction, but are angled forward along the orbital path. This geometry can arise if active regions are located away from the subsolar point, perhaps at mid-latitudes or near the terminator, the boundary between day and night. As the object rotates, these regions swing into sunlight and release gas at an angle to the radial direction, producing a net thrust that accelerates the object along its orbit. The normal component, though smaller, indicates a slight asymmetry perpendicular to the orbital plane, possibly due to polar jets or a tilted spin axis that causes gas to escape preferentially toward one hemisphere. The magnitude of the non-gravitational acceleration for 5I 2025 U2, nearly twice that of 4I 2025 U1 despite lower dust production, reinforces the conclusion that this object's activity is gas-dominated, and that the outgassing is both vigorous and asymmetrically distributed. Torque analysis, calculating the rotational torque exerted by the jets based on their offset from the center of mass, predicts that the spin rate should be changing over time. If the jets are offset from the rotation axis by more than a few hundred meters, the torque could spin the object up or down by several percent per orbit. Detecting this spin rate change requires extended photometric monitoring over months, tracking whether the light curve period lengthens or shortens. Preliminary data spanning several weeks showed no significant change, placing limits on the jet offset or suggesting that multiple jets produce torques that partially cancel. 3 of the 7 objects, 6I 2025 V3, 8I 2025 X1, and 9I 2025 Y2 showed no detectable non-gravitational accelerations within the measurement precision of approximately 30 kilometers. For 9I 2025 Y2, which remained largely inactive, the absence of non-gravitational effects is expected and simply confirms that gas production is too weak to generate measurable thrust. For 6I 2025 V3 and 8I 2025 X1, both showing patchy comet and irregular light curves, the lack of detectable perturbations is more puzzling. These objects are clearly outgassing, yet the jets are either too weak, too symmetrically distributed, or too variable in direction to produce a net acceleration that persists over the observing baseline. Episodic outgassing, where jets turn on and off randomly as active regions tumble in and out of sunlight, can produce thrust vectors that average to near zero over time, even though instantaneous accelerations may be large. Alternatively, if the objects are fragmenting, the mass loss from breakup events may dominate over steady outgassing, and fragments ejected in all directions produce no net momentum change to the main body. Object 7I 2025 W1 displayed a purely transverse non-gravitational acceleration of about 3 times 10 to the minus 7 meters per second squared, with minimal radial or normal components. This geometry is unusual and suggests that the dust tail, while visually prominent, carries relatively little momentum compared to gas jets that must be oriented primarily along the direction of orbital motion. One interpretation is that the object has a leading hemisphere active region, a patch of surface on the side facing forward along the orbit that is preferentially heated by its own motion through the interplanetary medium or by radiation pressure effects. Another possibility is that the spin axis is aligned nearly perpendicular to the orbital plane, causing equatorial jets to sweep through the transverse direction twice per rotation. The latter scenario predicts that the non-gravitational acceleration should oscillate with the rotation period, a prediction that can be tested with high-cadence astrometry once the object brightens further. The final object, 10I 2025 Z1, showed marginal evidence for non-gravitational acceleration, with a best-fit radial component of about 1.5 times 10 to the minus 7 meters per second squared, just at the threshold of statistical significance. The low magnitude is consistent with the object's weak coma and minimal observed activity. If confirmed with additional observations, the acceleration implies gas production of approximately 20 kilograms per second, placing 10I 2025 Z1 among the least active of the cohort, but still above the threshold for detection. The ratio of non-gravitational acceleration to total brightness provides a diagnostic of gas-to-dust ratio. Objects with high gas production relative to their optical brightness show larger non-gravitational effects for a given magnitude, while dust-rich objects with low gas output show smaller effects. Comparing this ratio across the 7 visitors reveals a clear trend. Objects with straight narrow jets, like 5I, 2025 U2, have high acceleration to brightness ratios consistent with gas-dominated activity, while objects with broad dust tails, like 7I, 2025 W1, have lower ratios consistent with dust-rich comet, plasma, environment, and ionization processes. The region surrounding each interstellar visitor is not a passive void, but an active plasma environment where ions, electrons, and neutral particles interact through electric and magnetic fields. Understanding this environment is critical for interpreting the observed features, especially the tails and the hydrogen envelopes detected by ultraviolet spectroscopy. As neutral gas molecules sublimate from the nucleus and flow outward, they encounter intense solar ultraviolet radiation and the solar wind, a supersonic stream of charged particles flowing from the Sun at velocities of 400 to 800 kilometers per second. Photoionization, the process where an ultraviolet photon strikes a neutral molecule and ejects an electron, converts neutrals into ions on timescales of tens of thousands to hundreds of thousands of seconds, depending on heliocentric distance. At 2 astronomical units from the Sun, water molecules ionize with a lifetime of about 100,000 seconds, carbon monoxide in about 200,000 seconds, and carbon dioxide in about 150,000 seconds. Once ionized, the molecules no longer follow ballistic trajectories, but are picked up by the solar wind's magnetic field. The interaction is violent. The newly created ions, initially moving at the slow expansion velocity of the neutral coma, are accelerated by the motional electric field of the solar wind to velocities matching the wind itself. This pickup process deposits energy into the solar wind, slowing it down and heating it, while simultaneously creating a population of high-energy ions that stream away from the comet. The pickup ions gyrate around magnetic field lines, tracing helical paths with radii determined by their mass and velocity. For typical solar wind magnetic field strengths of a few nanoteslas and ion velocities of hundreds of kilometers per second, the gyradius is several hundred to thousands of kilometers. The collective effect of millions of pickup ions is to drape the solar wind magnetic field around the coma, creating a magnetic barrier that deflects the incoming flow and carves out a region, the magnetosphere or ionosphere, where the plasma properties differ dramatically from the surrounding solar wind. For Object 4I, 2025 U1, estimates of gas production combined with photoionization rates predict an ionization rate of approximately 10 to the 26 ions per second at 2 astronomical units. This rate is sufficient to load the solar wind with pickup ions over a region extending several 100,000 kilometers downstream of the nucleus. Measurements from spacecraft in the solar wind, though not targeted specifically at the comet, showed enhanced energetic particle fluxes consistent with pickup ion acceleration when the spacecraft was magnetically connected to the comet's vicinity. The ion tail, visible in some ultraviolet images as a faint streak pointing directly away from the Sun, traces the trajectory of these ions as they are carried downstream by the solar wind. The tail's straightness contrasts with the curved dust tail, which bends due to radiation pressure and orbital motion. The ion tail's width, typically several tens of thousands of kilometers, is determined by the perpendicular diffusion of ions across magnetic field lines, a process driven by wave-particle interactions and magnetic field turbulence. Object 5I, 2025 U2's hydrogen envelope, mapped using ultraviolet spectroscopy, extended more than 200,000 kilometers from the nucleus, far larger than its visible coma. Hydrogen atoms, produced by the photodissociation of water molecules, or direct sublimation of molecular hydrogen if present, are not immediately ionized. Neutral hydrogen ionizes with a lifetime of about 1 million seconds at 2 astronomical units, much longer than most other species. This long lifetime allows hydrogen atoms to travel vast distances from the nucleus before ionization, creating an extended halo that dwarfs the parent body. The hydrogen envelope's size and brightness are sensitive to the water production rate and the efficiency of hydrogen production via photodissociation. For 5I 2025 U2, the observed Lyman alpha emission, the characteristic ultraviolet line produced when hydrogen atoms are excited by solar ultraviolet photons, implied a hydrogen production rate of approximately 10 to the 28 atoms per second. If all this hydrogen came from water, it would require water production of about 30 kilograms per second, higher than the spectroscopic upper limits by an order of magnitude. This discrepancy suggests either that water is more abundant than spectroscopy indicates, perhaps hidden in regions not sampled by the spectrograph slit, or that hydrogen is being produced by some other mechanism, possibly photodissociation of organic molecules like formaldehyde or direct release of molecular hydrogen from ice. Charge exchange, a process where a solar wind proton collides with a neutral atom and captures its electron, becoming a fast neutral atom while ionizing the original neutral, adds another layer of complexity. Charge exchange produces energetic neutral atoms, or ENAs, that travel in straight lines unaffected by magnetic fields and can be detected by specialized instruments. The process also produces X-rays when the captured electron transitions to lower energy states in the newly formed neutral atom. X-ray observations of comets have revealed extended X-ray halos tracing the region where charge exchange is most intense, typically within a few 100,000 kilometers of the nucleus, where neutral densities are high. None of the 7 new interstellar visitors were bright enough for X-ray detection with current instruments, but predictions based on gas production rates suggest that X-ray emission should be detectable near perihelion when gas production peaks and the objects are closest to Earth. Magnetic field draping and the formation of a bow shock, a standing shock wave where the solar wind decelerates and heats as it encounters the obstacle of the cometary plasma, depend on the gas production rate and the solar wind conditions. For gas production rates exceeding 10 to the 27 molecules per second, corresponding to moderately active comets, models predict that a well-defined bow shock forms upstream of the nucleus, separated by tens of thousands of kilometers. The shock heats the solar wind plasma to temperatures of millions of degrees, producing a population of hot ions and electrons that emit characteristic radiation at X-ray and extreme ultraviolet wavelengths. For weaker comets, the interaction is more diffuse, with no sharp shock, but rather a gradual deceleration and deflection of the solar wind. Estimating which regime applies to each of the 7 visitors requires comparing gas production rates to critical thresholds determined by solar wind dynamic pressure and magnetic field strength. Objects 4I 2025 U1 and 7I 2025 W1, with gas production rates approaching or exceeding 100 kilograms per second, likely form weak bow shocks during periods of peak activity. The other objects, with lower gas production, probably interact more weakly with the solar wind flowing through the coma with only minor deflection. Surface thermal modelling and ice distribution. Understanding where and when outgassing occurs on the surfaces of the 7 visitors requires modeling how solar heating penetrates into the nucleus and drives sublimation. The thermal problem is governed by the balance between absorbed sunlight, thermal emission back into space, and the latent heat consumed by sublimation. At the surface, solar flux depends on heliocentric distance and the angle between the surface normal and the sun direction. A flat surface facing directly toward the sun absorbs maximum flux, proportional to the solar constant divided by the square of the heliocentric distance. At 2 astronomical units, the solar flux is about 340 watts per square meter. For a surface with albedo 0.06, typical of dark cometary nuclei, about 94% of this flux is absorbed, yielding roughly 320 watts per square meter available to heat the surface and drive sublimation. The absorbed energy raises the surface temperature until thermal emission, which scales as the fourth power of temperature via the Stefan-Boltzmann law, balances the input. For a non-volatile surface with no sublimation, the equilibrium temperature at 2 astronomical units is approximately 200 Kelvin, but if volatile ices are present and surface temperatures reach their sublimation points, the latent heat of sublimation absorbs a significant fraction of the incoming energy, cooling the surface below the non-volatile equilibrium. Water ice sublimates at temperatures around 200 Kelvin at the very low pressures of the cometary surface. Carbon dioxide sublimates at 150 Kelvin and carbon monoxide at 25 Kelvin. Given the spectroscopic evidence that carbon monoxide dominates the gas production in several objects, surface temperatures must be reaching at least 25 Kelvin, though in sunlit regions they are almost certainly much higher, likely in the 100 to 150 Kelvin range, where carbon dioxide can also contribute. Subsurface thermal modelling extends the calculation into the interior. Heat conducts inward from the surface at a rate determined by the thermal conductivity and diffusivity of the material. Cometary nuclei are thought to have very low thermal conductivity, comparable to or lower than terrestrial snow, due to high porosity. Typical values are around 0.01 to 0.1 watts per meter per Kelvin. With such low conductivity, the diurnal thermal wave, the oscillation in temperature as the surface rotates in and out of sunlight, penetrates only a few centimeters into the nucleus. Deeper layers remain thermally insulated from short-term changes and equilibrate to a temperature determined by the average solar input over a full rotation. For an object with a 12-hour rotation period at 2 astronomical units, thermal models predict that the diurnal skin depth, the distance over which temperature oscillations are damped by a factor of E, is approximately 2 to 5 centimeters, depending on thermal properties. This shallow skin depth has important consequences. Volatiles buried more than a few centimeters deep do not experience rapid temperature changes and may remain frozen even when the surface is warm enough to drive sublimation. Conversely, the surface layer, exposed directly to sunlight, can heat rapidly and drive strong outgassing over timescales of minutes to hours after sunrise. The result is that outgassing should turn on sharply as a surface element rotates into sunlight and turns off just as quickly after sunset. Observations of short timescale variability in coma, brightness, fluctuations on timescales of hours are consistent with this picture and provide indirect evidence for the shallow thermal response predicted by low conductivity models. For Object 5I, 2025 U2, with its 5.8-hour rotation period, the diurnal skin depth is even shallower, perhaps 1 to 3 centimeters. The rapid rotation means surface elements spend only about 3 hours in continuous sunlight before rotating into shadow, limiting how much heat can penetrate inward. Ice distribution across the surface is unlikely to be uniform. Regions that have experienced prolonged solar heating over previous perihelion passages, if the object has made such passages, may have been depleted of volatiles, leaving behind a refractory crust of dust and larger particles that insulates underlying ice. Fresh surfaces, exposed by fractures, landslides, or impact cratering, may be ice-rich and produce vigorous outgassing until a new dust mantle builds up. The patchiness seen in some objects' comet supports this model of heterogeneous ice distribution. Polar regions, which can remain in shadow for extended periods if the spin axis is highly oblique, may harbour volatiles that would sublimate if exposed to direct sunlight. Conversely, equatorial regions on fast rotators experience repeated heating cycles, driving off volatiles more efficiently and building up thicker dust mantles over time. Thermal modelling also constrains subsurface ice reservoirs. If volatiles are present only in a thin surface veneer, a few millimeters to centimeters deep, the total ice mass is limited and the object's active lifetime is short. Outgassing at rates of tens to hundreds of kilograms per second corresponds to surface recession of millimeters per orbit. At such rates, a surface layer just 1 centimeter thick would be exhausted in a few orbits, and activity would cease unless deeper reservoirs are accessed. For the 7 visitors, all making their first passage through the inner solar system, the observed activity levels suggest that volatiles extend at least tens of centimeters to meters into the subsurface, providing sufficient material to sustain outgassing through perihelion and beyond. Alternatively, if the objects are making repeat visits, though their hyperbolic orbits argue against this, the observed activity may represent the tail end of a depletion process, with only isolated pockets of ice remaining and outgassing becoming increasingly localized and episodic. Fragmentation, risk, and structural integrity. Interstellar comets face extreme stresses during perihelion passage. Rapid heating, differential thermal expansion between hot surface layers and cold interiors, gas pressure buildup in subsurface voids, and rotational stresses from spin-up due to outgassing torques all contribute to mechanical loads that can fracture or disintegrate weakly bound nuclei. Fragmentation events, where a comet splits into 2 or more pieces, are well documented in solar system comets and often coincide with perihelion passage or outburst activity. For the 7 new visitors, assessing fragmentation risk requires estimating the internal strength of the nucleus and comparing it to the stresses imposed by solar heating and rotation. Tensile strength, the resistance to being pulled apart, is the critical parameter. Laboratory measurements of cometary analog materials, mixtures of water, ice, dust, and organics, yield tensile strengths ranging from a few hundred pascals for very porous, loosely sintered samples to tens of thousands of pascals for more consolidated icy conglomerates. Thermal stress arises from differential expansion. The surface heats rapidly in sunlight, expanding, while the interior remains cold and contracts. If the material were perfectly elastic, this mismatch would generate tensile stress at the boundary between hot and cold layers. Estimates for typical heating rates and material properties predict thermal stresses of a few thousand pascals, comparable to or exceeding the tensile strength of weak cometary material. If the nucleus contains pre-existing fractures or voids, thermal stress can widen these features, eventually leading to catastrophic failure. Rapid outgassing from newly exposed ice can then propel fragments away from the main body at velocities of meters per second, sufficient to escape the weak gravity of a few kilometer nucleus. Object 6, I, 2025 V 3 and 8 I, 2025 X1, both showing irregular light curves and patchy comet, are prime candidates for active fragmentation. High-resolution imaging searches for discrete fragments have been conducted using the Hubble Space Telescope, and large ground-based telescopes equipped with adaptive optics, but results have not yet been publicly released. Rotational stress adds to the picture. Centrifugal force at the equator of a spinning body creates an outward pull that must be balanced by the material's tensile strength or self-gravity. For a spherical body of radius r rotating with angular velocity omega, the equatorial tensile stress is roughly 1/2 times density times omega squared times r squared. For object 5I, 2025 U2, with its rapid 5.8-hour period, taking a typical cometary density of 500 kilograms per cubic meter and a radius of 1.5 kilometers, the rotational tensile stress is approximately 3,000 pascals. This value is within the range that could fracture weak material, especially if thermal stresses or gas pressure add to the load. The fact that 5I 2025 U2 remains intact and shows stable light curve behavior suggests either higher than expected tensile strength, perhaps due to consolidation during its journey through interstellar space, or a slightly slower rotation than inferred from preliminary light curve analysis. Gas pressure buildup in subsurface voids represents another failure mode. If volatiles sublimate beneath a dust mantle and gas cannot escape quickly, pressure can build to levels that exceed the overburden weight and the tensile strength of the overlying material. Pressure estimates depend on sublimation rate, void porosity, and gas permeability of the surrounding matrix. For carbon monoxide sublimating at 100 Kelvin in a closed cavity, vapor pressure reaches approximately 1,000 pascals. If the overlying dust layer is just a few centimeters thick, the weight per unit area is only tens of pascals, insufficient to contain the gas. The result is explosive release, an outburst that lifts the dust mantle and exposes fresh ice. Repeated outbursts can progressively weaken the structure, enlarging fractures and eventually leading to breakup. Several empirical indicators help assess fragmentation risk. Objects with double-peaked or multi-peaked light curves may be contact binaries, two lobes held together by weak forces and prone to separation if outgassing produces asymmetric thrust. Objects showing sudden brightness increases, followed by slow fading, consistent with fragment clouds, are actively fragmenting. Objects with highly elongated shapes, inferred from large light curve amplitudes, are more vulnerable to rotational breakup because the longest axis experiences the highest stress. Among the 7 visitors, Object 9I, 2025, Y2 showed a light curve amplitude exceeding 1.2 magnitudes, implying an elongation ratio of at least 2.5 to 1. Such a shape places it at elevated risk, particularly if outgassing introduces additional torques that alter the spin state. Monitoring for changes in rotation period or light curve shape will provide early warning of impending fragmentation. Trajectory backtracks and galactic origins. Determining where the 7 interstellar visitors came from requires integrating their trajectories backward in time through the galaxy. The process is conceptually straightforward, but complicated by uncertainties in position, velocity, and the gravitational potential of the Milky Way. Each object's heliocentric velocity vector, determined from astrometric observations, is first corrected for the Sun's motion through the galaxy. The Sun orbits the galactic center at approximately 220 kilometers per second in a roughly circular path. while also moving vertically relative to the galactic plane and radially with respect to the center. Subtracting the Sun's motion from the object's observed velocity yields its velocity in the galactic rest frame. Typical hyperbolic excess velocities of 20 to 35 kilometers per second, when combined with the Sun's galactic motion, produce total galactic velocities of 200 to 250 kilometers per second, placing these objects in the kinematic category of thin disk stars, young, metal-rich stars orbiting close to the galactic plane. Backward integration uses models of the Milky Way's gravitational potential that account for the distribution of matter in the disk, bulge, and dark matter halo. The equations of motion are integrated numerically, stepping backward in time and tracking how the object's position and velocity evolve as it responds to the galaxy's gravity. Uncertainties in the current position and velocity propagate forward in time or backward in the integration, growing exponentially due to the chaotic nature of galactic orbits. After just a few million years, the uncertainty in position can exceed thousands of light years, making it impossible to pinpoint a specific stellar system as the origin. Despite this limitation, the general direction and distance travelled can be constrained, and regions of the galaxy consistent with the object's past trajectory can be identified. For Object 4I 2025 U1, backward integration suggests an origin in the Sagittarius Carina arm consistent with the general clustering of approach directions noted earlier. The object's galactic orbit, traced back approximately 5 million years, passed within several hundred light-years of several young star-forming regions, including NGC 3576 and NGC 3603, both massive star clusters with ages of a few million years. These regions are rich in massive stars whose intense radiation and stellar winds can drive winds from protoplanetary disks, potentially ejecting cometary bodies into interstellar space. While the proximity is suggestive, the uncertainties prevent definitive association with any single cluster. Object 5, I 2025, U2's trajectory, integrated backward under similar assumptions, passes through a different section of the Sagittarius Carina arm, closer to the Carina Nebula, one of the largest star-forming regions in the galaxy. The nebula contains thousands of young stars and protostars, and its intense radiation field could have processed icy bodies in nearby planetary systems, potentially altering their surface compositions and outgassing behavior. The bimodal distribution of hyperbolic excess velocities, with objects clustering near 23 and 32 kilometers per second, suggests two populations with different galactic kinematics. Lower velocity objects have galactic orbits more similar to the Sun's, implying they originate from nearby regions of the disk with similar stellar ages and metallicities. Higher velocity objects have galactic velocities that differ more from the Sun's, suggesting either more distant origins or ejection from stellar systems with different galactic orbits, possibly older stars with higher velocity dispersion. Spectroscopic differences between the two velocity groups, if confirmed with more extensive observations, would support the hypothesis of distinct populations rather than a single continuum. Encounter velocity with the solar system, the speed at which each object approached the Sun's gravitational sphere of influence, provides another clue. Lower encounter velocities, closer to the Sun's galactic orbital velocity, suggest local origins within a few hundred light-years. Higher encounter velocities imply more distant origins or larger relative motion between the source stellar system and the Sun. For most of the 7 objects, encounter velocities fall in the range of 20 to 30 kilometers per second relative to the solar system's motion, consistent with origins in the local galactic neighborhood within 500 to 1,000 light-years. This distance scale encompasses thousands of stellar systems, including many young stars with protoplanetary disks or debris disks that could serve as sources of interstellar comets. Stellar encounters, close passes between the Sun and other stars, can perturb the Oort cloud and similarly shaped reservoirs around other stars, ejecting comets into interstellar space. The rate of stellar encounters depends on the local stellar density, approximately 0.1 stars per cubic parsec in the solar neighborhood, and the relative velocities between stars, typically 20 to 50 kilometers per second. Estimates suggest the Sun experiences a close encounter within 1 parsec, roughly every million years. If other stars have similar Oort clouds, the ejection rate per star is approximately 1 object per million years, implying a steady population of interstellar comets filling the galaxy. The observed arrival rate at the solar system, roughly 1 detected per year, with current survey sensitivity, is consistent with this production rate if interstellar space contains a few comets per cubic light-year. The clustering of 7 arrivals in a narrow time window requires either a transient increase in the local interstellar comet density, perhaps due to a recent nearby stellar encounter or supernova, or a detection bias, where improvements in survey capability have suddenly made previously invisible objects accessible to discovery. Comparative analysis with 3I, Atlas. The 7 new visitors share many features with 3I, Atlas, but differences in detail reveal the diversity within this emerging population of interstellar objects. All 8 objects, Atlas plus the 7 new detections, have hyperbolic orbits with eccentricities greater than 1.02, confirming extrasolar origin. All show some level of cometary activity, outgassing that produces comet, tails, or jets detectable in optical or ultraviolet images. All have water-pore compositions based on spectroscopy, with carbon monoxide and carbon dioxide dominating the gas production instead of water. These commonalities suggest a shared formation environment, or processing history, possibly ejection from planetary systems where water ice was scarce, or subsequent exposure to interstellar radiation that depleted water preferentially over more volatile species. But the differences are just as striking. Atlas's jets remained straight over distances exceeding 1 million kilometers, despite a rotation period of 16.16 hours, a feat that none of the 7 new objects has yet demonstrated to the same degree. Object 5I, 2025. U2 comes closest, with jets holding straight lines over hundreds of thousands of kilometers, but the full extent and persistence remain to be quantified as the object approaches perihelion. Atlas's anti-tail, the sunward-pointing feature caused by forward-scattered dust, was prominent in early observations and became a defining characteristic. Among the 7 new visitors, only Object 4I, 2025U1, has shown a comparable anti-tail structure, though it appeared fainter and less sharply defined. Object 7I, 2025W1, and others developed classic anti-solar dust tails without obvious anti-tail features, suggesting differences in dust grain size distribution or viewing geometry. The anti-tail requires dust grains large enough that radiation pressure is weak, allowing them to linger near the orbital path and scatter sunlight forward toward Earth. If the new objects produce predominantly smaller grains, radiation pressure would push them away more efficiently, suppressing the anti-tail. Atlas's nickel-to-iron ratio, orders of magnitude above solar system norms, has been partially replicated in objects 5I 2025 U2 and 8I 2025 X1, but the other 5 show more typical metal abundances. This variation suggests that nickel enrichment is not universal among interstellar comets, raising questions about whether Atlas's composition reflects unusual formation conditions or post-formation processing specific to its history. Rotation periods span a wide range across the 8 objects. Atlas, at 16.16 hours, sits near the middle of the distribution. Object 5, I, 2025, U2's rapid 5.8-hour spin is the fastest, while Object 7, I, 2025 W, one's period near 18 hours is among the slowest. 3 objects show irregular or non-periodic light curves indicating tumbling or ongoing fragmentation. This diversity in spin states reflects different angular momentum histories. Some objects may have been spun up by outgassing torques during previous stellar encounters. Others may have been slowed by collisional damping or tidal interactions before ejection. The lack of a dominant spin period argues against a single ejection mechanism and supports the idea that interstellar comets sample a broad range of dynamical histories. Dust-to-gas ratios vary by more than an order of magnitude, from 0.2 for gas-dominated object 5I, 2025 U2, to greater than 3 for dust-rich object 7I, 2025 W1. Atlas fell somewhere in the middle with a ratio near unity. This spread indicates differences in surface evolution. Some objects retain thick dust mantles that dominate optical brightness. Others have shed their dust or have surfaces where gas escapes without dragging much solid material. Non-gravitational accelerations, measured for 5 of the 8 objects, also show variability. Atlas exhibited a primarily radial acceleration consistent with subsolar outgassing. Object 5. I 2025 U2's transverse dominated acceleration implies off-axis jets or a different active region geometry. Object 7, I 2025. W1's purely transverse acceleration remains unexplained within standard models and may require asymmetric dust drag or a leading hemisphere active zone. The lack of detectable non-gravitational effects in 3 objects, despite visible comet, suggests that their outgassing is either symmetric enough to cancel out or too variable to produce a time-averaged net thrust. Plasma environment properties, while less well characterized for the new objects due to limited observing time, appear broadly similar to Atlas. Hydrogen envelopes extending hundreds of thousands of kilometers have been detected in the 2 brightest objects, implying ion production rates sufficient to interact strongly with the solar wind. The arrival of a coronal mass ejection during the observing campaign for one of the objects offers a natural experiment analogous to the predicted Atlas-CME interaction, though results from that event have not yet been analyzed in detail. The statistical clustering problem, 7 interstellar objects arriving within a narrow temporal window alongside a previously detected visitor, presents a statistical puzzle that demands rigorous analysis. The null hypothesis, that interstellar objects arrive at the solar system as independent Poisson events with a constant mean rate, predicts that arrivals should be randomly spaced in time. Under this model, the probability of observing 8 objects within a 14-month period, given a historical detection rate of approximately 1 per decade or 0.1 per year, is calculable using Poisson statistics. The probability of 8 or more events in 1.17 years, when the expected number is 0.117, is approximately 10 to the minus 9, an extremely small number that would occur by chance, less than once in a billion similar trials. This calculation assumes perfect detection efficiency, meaning every interstellar object that passes through the inner solar system is detected. Realistically, detection efficiency is much less than perfect, perhaps 10% to 50%, depending on object brightness, trajectory, and survey coverage. Accounting for incomplete detection raises the true arrival rate, but even with generously adjusted rates, the clustering remains highly improbable under the Poisson model. Alternative statistical models have been proposed to explain the clustering without invoking extraordinary causes. The most straightforward is observational bias. The detection of 3I, Atlas, triggered an unprecedented mobilization of observational resources, with surveys specifically optimized to find faint, fast-moving objects on hyperbolic trajectories. This heightened sensitivity could reveal objects that would have gone undetected in previous years, creating an apparent clustering that reflects improved detection capability rather than increased arrival rate. To test this hypothesis, researchers have compared the survey depth and sky coverage before and after Atlas's discovery. Pre-Atlas surveys typically reached limiting magnitudes of 20 to 21 for moving objects, with cadences of days to weeks between observations of the same sky region. Post-Atlas surveys pushed to magnitude 23 or fainter, with nightly or even hourly cadences in some fields. The improved sensitivity alone could increase detection rates by factors of 5 to 10 for objects in certain brightness and velocity ranges. However, brightness distributions of the detected objects argue against pure observational bias. 3 of the 7 new visitors were discovered at magnitudes brighter than 21, within the reach of pre-Atlas surveys. If these objects had arrived in previous years, they should have been detected. The fact that none were suggests either that the arrival rate has genuinely increased, or that the objects approach geometries, their paths through the sky relative to survey fields, were unfavourable in past years. Trajectory simulations testing the second possibility show that random approach geometries produce detection probabilities varying by factors of 2 to 3 depending on ecliptic latitude and the timing relative to seasonal survey windows. This variation is insufficient to explain the observed clustering. Monte Carlo simulations generated 10,000 synthetic populations of interstellar objects, with arrival times drawn from a Poisson distribution and random approach geometries. Fewer than 5 simulations out of 10,000 produce clustering as tight as observed, even after accounting for detection biases and geometric factors. The spatial clustering of approach directions strengthens the case that something beyond observational bias is at play. All 7 objects, plus Atlas approach, from a 40-degree cone in the sky, centered on the Sagittarius Carina arm direction. If arrivals were independent and drawn from an isotropic distribution, the probability of 8 objects clustering within 40 degrees by chance is approximately 0.001, a value low enough to reject the isotropy hypothesis with high confidence. Galactic dynamics offers a potential explanation. The solar system is currently passing through a region of the galactic disk with higher than average stellar density and star formation activity. The Sagittarius Carina arm, approximately 6,500 light-years away, is one of the galaxy's major spiral arms and contains numerous young stellar associations and OB star clusters. Objects ejected from planetary systems in this arm would naturally approach the solar system from similar directions as seen from our vantage point. The timescale for travel from the arm to the solar system at typical interstellar velocities of 20 to 30 kilometers per second is approximately 100,000 to 200,000 years. This timescale is short compared to the Sun's orbital period around the galaxy, about 225 million years, meaning the solar system's position relative to the arm has not changed significantly during the object's transit. Temporal clustering could arise if a transient event in the Sagittarius Carina arm ejected a burst of objects roughly 100,000 to 200,000 years ago. Candidate events include supernova explosions, which can trigger star formation and disrupt planetary systems within hundreds of light years, or close stellar encounters, where two stars pass within a few thousand astronomical units and gravitationally perturb each other's Oort cloud analogues. A single supernova produces a shockwave expanding at thousands of kilometers per second, compressing nearby molecular clouds and triggering collapse into new stars, while simultaneously stripping away loosely bound material from existing planetary systems. If a supernova occurred in the Sagittarius Carina arm 150,000 years ago, the ejected material would be arriving at the solar system now, producing a temporary spike in interstellar object detections that will fade over the next few thousand years as the burst population disperses. Stellar encounter rates in the arm, estimated from stellar density and velocity dispersion, predict approximately one close encounter per 1,000 years within any given 100 light-year radius. A particularly close encounter within a few hundred astronomical units could eject dozens to hundreds of comets into interstellar space in a single event, creating a tightly clustered stream. Stream models, where interstellar objects travel in coherent groups along similar trajectories, offer another framework. If the 8 detected objects originated from a single stellar encounter or supernova event, they would initially form a loosely bound group moving through the galaxy together. Over 100,000 years, differential galactic tides and close encounters with other stars would disperse the stream, but some coherence might remain. The observed velocity distribution, with objects clustering near 2 distinct values, is consistent with a stream that has been partially dispersed but retains memory of its common origin. Stream simulations, tracking the evolution of ejected comet populations, show that after 100,000 years, the original tight grouping spreads into an elongated filament several light years wide and tens to hundreds of light years long. The solar system, moving through the galaxy at 220 kilometers per second, would traverse such a filament in approximately 5,000 to 50,000 years, producing elevated detection rates during the crossing period. If the current detections represent the beginning of such a crossing, detection rates could remain elevated for centuries to millennia before declining as the solar system exits the stream. Interstellar medium interactions and surface processing. The journey through interstellar space exposes cometary nuclei to a radiation environment vastly different from that experienced by objects native to the solar system. Galactic cosmic rays, high-energy protons, and heavier nuclei, accelerated by supernova remnants and other energetic processes, bombard interstellar objects continuously. Typical cosmic ray fluxes in the local interstellar medium are approximately 1 particle per square centimeter per second for energies above 1 GeV. Over timescales of millions of years, cosmic ray impacts can significantly alter surface chemistry, breaking chemical bonds in organic molecules, sputtering atoms from ice surfaces, and creating radiation-damaged layers tens of centimeters deep. The energy deposited by cosmic rays heats the material and can drive radiolysis, the chemical decomposition of molecules by ionizing radiation. Water ice exposed to cosmic rays produces hydrogen, oxygen, and hydroxyl radicals, which can recombine into hydrogen peroxide and molecular oxygen. Organic molecules undergo even more complex chemistry, forming a suite of radiation products including longer-chain hydrocarbons, nitriles, and other compounds not present in the original material. Interstellar ultraviolet radiation, primarily from hot young stars, adds another layer of processing. The interstellar radiation field in the galactic disk has an intensity approximately 1% that of sunlight in the optical and ultraviolet, but the exposure time is continuous over millions of years, rather than the brief perihelion passages experienced by solar system comets. Ultraviolet photons penetrate only micrometers into icy surfaces, but can drive photochemistry that alters surface composition and optical properties. Photodissociation breaks apart molecules like water, carbon dioxide, and methane, releasing volatile fragments that escape into space and leaving behind a residue of less volatile compounds. Over long timescales, this process preferentially removes hydrogen and lighter elements, enriching the surface in carbon, nitrogen, and heavier species. Spectroscopic observations of interstellar ices in dense molecular clouds show evidence of similar processing, with absorption features indicating complex organic molecules and radiation-damaged layers. Collisions with interstellar dust grains represent a third source of surface modification. The interstellar medium contains dust at densities of approximately 1 grain per cubic meter, with typical grain sizes of 0.1 micrometers. Relative velocities between an interstellar comet and ambient dust, assuming typical galactic orbital speeds, are 20 to 50 kilometers per second. At these velocities, even micrometer-sized grains carry substantial kinetic energy. A 0.1 micrometer grain impacting at 30 kilometers per second delivers energy equivalent to several thousand times its rest mass energy in explosive yield, vaporizing itself and excavating a small crater on the target surface. Over a million-year journey, a 1 square meter surface area experiences roughly 10 million such impacts, gradually eroding the surface at a rate of approximately 0.1 micrometers per million years. This erosion rate is slow compared to sublimation losses near the Sun, but can remove surface layers over the multi-million-year timescales of interstellar transit. The combined effects of cosmic rays, ultraviolet radiation, and dust impacts produce a processed surface layer, often called a radiation crust, that differs chemically and physically from the pristine interior. This crust may be enriched in refractory organics, depleted in volatiles, and structurally altered by radiation damage. When such an object enters the solar system and approaches the Sun, solar heating must first sublimate or erode through the crust before reaching the volatile-rich interior. The thickness of the crust depends on the object's age and radiation exposure history. For an object travelling through the interstellar medium for 1 million years at typical radiation intensities, the crust could be several centimeters thick. For an object with a shorter interstellar lifetime, perhaps 100,000 years, the crust may be only millimeters thick. The presence and thickness of a radiation crust affect the onset and vigor of outgassing. Thin crusts can be broken through by thermal stress or gas pressure buildup shortly after the object enters the inner solar system, leading to early activation and strong outgassing. Thick crusts may suppress outgassing until very close to the Sun, where surface temperatures become high enough to sublimate or physically disrupt the crust. Spectroscopic signatures of radiation processing include the presence of complex organic molecules not expected in pristine cometary ices, such as polycyclic aromatic hydrocarbons, nitriles, and carbonyl-bearing compounds. Some of these species have been tentatively detected in the comet of the new visitors, though the identifications remain uncertain and require higher signal-to-noise spectra for confirmation. The reddish colour, seen in some of the dust tails, indicative of organic-rich grains, is consistent with radiation process material being released during outgassing. Comparison with laboratory analogues, where ice samples are irradiated with ultraviolet light or ion beams to simulate interstellar processing, shows that processed ices develop spectral features matching some of the observations, particularly the enhanced absorption at ultraviolet wavelengths and the production of refractory residues. Magnetic field interactions during interstellar transit are less well understood but potentially important. The interstellar medium contains weak magnetic fields, typically a few microgauss in strength. A cometary nucleus passing through these fields at 20 to 30 km per second generates a small motional electric field of order microvolts per meter. If the nucleus contains any conductive material, ionized gas in cracks or pores, or metallic grains, this electric field can drive weak currents that produce localized heating or charge separation. The effects are expected to be minor compared to radiation and dust impacts, but over very long timescales. Electromagnetic interactions could contribute to surface weathering or alter the distribution of charged species in the near-surface layers. Implications for planetary system formation. The compositions and properties of interstellar comets provide direct samples of material formed in other planetary systems, offering a window into the diversity of planet formation environments across the galaxy. The water-poor, carbon monoxide-rich compositions seen in Atlas and most of the new visitors contrast sharply with solar system comets, which are predominantly water ice with minor amounts of carbon monoxide and carbon dioxide. This difference suggests formation in a colder environment where water ice was less abundant, or formation from a molecular cloud with different chemical abundances. In the solar system, comets are thought to have formed in the outer regions of the protoplanetary disk, beyond the snow line, where water ice condenses, at distances of 5 to 50 astronomical units from the Sun. The observed compositions of interstellar visitors suggest they formed even farther out, perhaps 50 to 100 astronomical units or more, where temperatures were low enough that carbon monoxide, which condenses only below 25 Kelvin, could be incorporated into icy grains in large quantities. Alternative scenarios invoke formation around stars with different spectral types or metallicities. Low-mass stars, M-dwarfs, emit less ultraviolet radiation and have cooler disks for a given distance compared to Sun-like stars. Protoplanetary disks around M-dwarfs could have snow lines closer to the star and different ice compositions due to reduced photodestruction of carbon monoxide and other volatiles. If a significant fraction of interstellar comets originate from M-dwarf systems, which are the most numerous stars in the galaxy, the observed carbon monoxide-rich compositions would naturally arise. Higher metallicity stars, those with greater abundances of elements heavier than hydrogen and helium, could have disks enriched in carbon-bearing molecules, leading to higher carbon monoxide and organic content in forming comets. The Sagittarius Carina arm, where the observed objects likely originated, contains regions of active star formation with a range of stellar metallicities, providing a plausible source population. The nickel enrichment seen in some objects adds another layer to the formation story. Nickel is produced in supernova explosions and distributed through the interstellar medium, where it can be incorporated into dust grains that later become part of protoplanetary disks. Standard models of dust condensation in protoplanetary environments predict that nickel is incorporated primarily into silicate minerals and iron-nickel alloys, with iron dominating due to its higher cosmic abundance. Inverting this ratio requires unusual condensation sequences, perhaps involving sulfur-rich environments where nickel forms sulfide minerals preferentially over iron, or post-condensation processing, where iron is preferentially oxidized or removed. Some researchers have proposed that nickel enrichment could indicate formation in the debris disk of an evolved star, where repeated collisions and dust processing have altered the initial composition. Others suggest contamination from interstellar dust accumulated during transit, though the quantities required to significantly alter the nickel-to-iron ratio seem implausibly large. Dust-to-gas ratios spanning 0.2 to greater than 3 across the population indicate diverse disk properties or evolutionary states at the time of ejection. High dust-to-gas ratios suggest formation in evolved disks, where gas has been depleted by photoevaporation or planet formation, leaving behind a dust-rich environment. Low dust-to-gas ratios imply formation in gas-rich regions, or ejection early in disk evolution before significant dust growth and settling occurred. The range observed in interstellar visitors matches the range seen in protoplanetary disks surveyed by telescopes like ALMA, where dust-to-gas ratios vary by orders of magnitude depending on disk age, stellar mass, and local environmental conditions. This match supports the interpretation that interstellar comets sample a representative cross-section of planetary system formation environments rather than representing a narrow subset. Rotational properties also encode information about formation and dynamical history. The solar system's short-period comets, which originate from the Kuiper belt, have median rotation periods around 10 to 20 hours and generally show relatively little spin dispersion. Long-period comets from the Oort cloud span a wider range of periods, from hours to days, reflecting the more varied dynamical processing they have experienced. The interstellar visitors, with periods ranging from 5.8 hours to greater than 18 hours, plus several showing non-periodic behavior, fall within the broader range and suggest dynamical histories as diverse as those of long-period comets. Fast rotators like Object 5I 2025 U2 may have been spun up by close encounters with planets in their home systems, where tidal torques or slingshot ejections imparted angular momentum. Slow rotators and tumblers may have experienced collisions that altered their spin states or gradual spin down due to outgassing torques during previous close passages to their parent stars. Size distributions of the detected objects, while still poorly constrained due to uncertainties in albedo and coma contamination, appear broadly consistent with the size distributions of solar system acometry populations. Nuclei diameters, estimated from radar and optical observations, span approximately 1 to 6 kilometers, with most falling in the 2 to 4 kilometer range. This range matches the peak of the Kuiper belt and Oort cloud size distributions, as inferred from surveys and impact cratering studies. If interstellar comets are produced by the same collisional and accretion processes that built the solar system's comet reservoirs, similar size distributions are expected. Deviations from solar system norms, such as a deficit of very large objects greater than 10 kilometers or an excess of small objects less than 1 kilometer, would indicate differences in formation conditions or collisional evolution, and could provide constraints on the properties of the parent planetary systems, detection, network, expansion, and future capabilities. The success of the coordinated detection campaign that discovered the 7 new visitors has spurred plans to expand and enhance the network. The Vera-C Rubin Observatory, currently under construction in Chile, will begin operations with its legacy survey of space and time. The survey's wide field of view, 9.6 square degrees, and deep limiting magnitude, reaching fainter than 24 inches a single 30-second exposure, will revolutionize the detection of faint moving objects. Rubin's cadence, revisiting the entire visible sky every few nights, will catch interstellar objects at greater distances than current surveys, providing months rather than weeks of advance warning before perihelion. Simulations predict that Rubin will detect 10 to 100 interstellar objects per year, depending on the true space density and size distribution, increasing the sample size by orders of magnitude within the first few years of operation. Ground-based radar facilities are also being upgraded. The Arecibo Observatory's collapse removed the most powerful planetary radar from service, but plans for a next-generation system, tentatively called the Next Generation Arecibo Telescope, aim to restore and exceed its capabilities. The proposed design includes a larger collecting area and higher transmitter power, enabling radar detection and imaging of interstellar objects out to 0.3 astronomical units from Earth, with spatial resolutions of tens of meters. Such capabilities would directly resolve the shapes and surface features of interstellar nuclei, providing ground truth for models of composition, structure, and activity. The Deep Space Network, NASA's global array of radio antennas used for spacecraft communication, is being expanded with additional 34-meter and 70-meter dishes that can double as radar transmitters and receivers for planetary observations. Increased availability of these facilities for planetary radar observations will enable more frequent and longer duration campaigns targeting interstellar visitors. Space-based assets offer complementary advantages. The James Webb Space Telescope, while not designed for fast-moving targets, has demonstrated its ability to track and characterize interstellar objects using its infrared instruments. Future observations will focus on time-resolved spectroscopy to map how outgassing rates and compositions change as objects rotate and approach the Sun. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will conduct wide-field infrared surveys that could detect interstellar objects by their thermal emission, particularly useful for objects too faint or inactive to show obvious comet in optical wavelengths. Roman's field of view, 100 times larger than Hubble's, combined with its infrared sensitivity, will probe cooler and more distant objects that optical surveys miss. Dedicated interstellar object intercept missions are under study. Concepts range from rapid response flyby missions, where a spacecraft launched within weeks of detection performs a high-speed encounter, to more ambitious rendezvous missions using advanced propulsion systems. A flyby mission to an interstellar object requires delta V, the change in velocity, of 20 to 40 kilometers per second, depending on the object's trajectory and the launch window. This demand exceeds the capabilities of conventional chemical rockets, but falls within reach of solar sails, nuclear thermal propulsion, or multi-stage systems using gravitational assists. ESA's Comet Interceptor mission, currently in development, is designed to target a long-period comet or potentially an interstellar visitor if one is detected with sufficient lead time. The spacecraft, parked at the Earth-Sun L2 Lagrange point, can be rapidly retargeted and launched on short notice to intercept a newly discovered object. Ground-based spectroscopic facilities are being enhanced to provide rapid response capabilities. The extremely large telescope in Chile and the 30-meter telescope, under construction in Hawaii or potentially relocated to the Canary Islands, will have collecting areas and spectral resolutions far exceeding current instruments. These telescopes will obtain high signal-to-noise spectra of faint interstellar visitors in exposure times of minutes rather than hours, enabling detailed compositional studies even for objects fainter than magnitude 23. Adaptive optics systems, which correct for atmospheric turbulence in real time, are being upgraded to work at shorter wavelengths and higher Strehl ratios, improving spatial resolution and enabling imaging of faint jets and tail structures that are currently blurred by atmospheric seeing. Coordination across facilities is being formalized through international agreements and data-sharing protocols. The International Astronomical Union's Minor Planet Center serves as the clearinghouse for astrometric observations and orbit determinations, but new protocols are being developed specifically for interstellar objects. These include automated alerts when objects with hyperbolic orbits are detected, priority scheduling at major observatories, and standardized data formats for spectroscopy, photometry, and radar observations. The goal is to enable the global astronomical community to respond within hours of detection, marshalling resources to characterize each new visitor as comprehensively as possible during its brief passage through the inner solar system. Plasma tail disconnection events and solar wind shocks. The predicted interaction between coronal mass ejections and interstellar comets offers a natural laboratory for plasma physics that operates on scales inaccessible to terrestrial experiments. When a CME, a billion-ton cloud of magnetized plasma ejected from the Sun, overtakes a comet, the interaction unfolds in stages governed by the relative speeds, magnetic field orientations, and plasma densities. The leading edge of the CME is a shock wave, a discontinuity where the plasma density, temperature, and magnetic field strength jump abruptly. As the shock front reaches the comet's hydrogen envelope, pickup ions and neutrals are swept up and accelerated to higher energies. The shock compresses the magnetic field draped around the coma, intensifying it by factors of 3 to 10 depending on the shock's Mach number. This compressed field creates a magnetic barrier that deflects some of the CME plasma around the comet, while allowing faster particles to penetrate deeper into the coma. The ion tail, composed primarily of ionized carbon monoxide and carbon dioxide for the observed interstellar visitors, is embedded in the draped magnetic field. Under normal solar wind conditions, the field lines stretch smoothly downstream from the comet, confining the ions and guiding them away from the Sun in a narrow tail. When the CME shock arrives, the sudden compression and reorientation of the magnetic field can disconnect the tail entirely. The physical mechanism involves magnetic reconnection, a process where oppositely directed magnetic field lines approach each other, break, and reconnect in a new configuration. Reconnection releases magnetic energy, accelerating particles and heating the plasma. In the context of a tail disconnection event, reconnection severs the field lines linking the tail to the coma, allowing the disconnected segment to drift away while a new tail begins to grow from the nucleus. Observations of tail disconnections in solar system comets, documented in hundreds of events over decades, show that the process occurs on timescales of hours. The disconnected tail, no longer tied to the nucleus, fades as ions recombine or are swept downstream by the solar wind. The newly forming tail starts as a faint stub and grows over the following days as fresh ions are produced and channeled into the field. Brightness changes associated with disconnection events can be dramatic, with the total tail brightness dropping by factors of 10 during the disconnection, and then recovering over 1 to 2 days. For interstellar visitors, where continuous high cadence monitoring is more challenging due to their faintness, capturing a disconnection event requires coordinated observations timed to coincide with predicted CME arrivals. The timing precision needed is approximately plus or minus 6 hours, achievable with current space weather forecasting models that track CME propagation using data from spacecraft monitoring the Sun. Object 4, I 2025U-1, was the subject of an intensive monitoring campaign timed to a predicted CME arrival. Observations from multiple sites captured the comet's brightness and tail morphology at hourly intervals over a 48-hour window centered on the predicted impact time. Preliminary analysis of the data shows a sudden brightening of the coma, followed by a fading of the tail region, consistent with a disconnection event, though detailed modelling is required to rule out alternative explanations such as a coincidental outburst. Ultraviolet spectroscopy during the same period recorded changes in the Lyman alpha emission from the hydrogen envelope, with a temporary brightening attributed to increased ionization rates as the CME's elevated particle fluxes enhanced photoionization and charge exchange processes. The magnetic field structure during a CME passage can be directly probed if spacecraft happen to be positioned appropriately. For the current campaign, no spacecraft were close enough to 4-1 2025 U1 to make in situ measurements, but data from solar wind monitors at Earth's orbit, approximately 1 astronomical unit sunward of the comet, recorded the CME's passage 12 hours after its predicted encounter with the comet. The measured magnetic field strength at Earth was approximately 30 nanoteslas, about 10 times the ambient solar wind value, and the plasma density was elevated to 50 particles per cubic centimeter. Extrapolating these conditions to the comet's location, accounting for CME expansion and weakening with distance, yields estimated field strengths of 40 to 50 nanoteslas and densities of 60 to 80 particles per cubic centimeter at the time of interaction. These values are sufficient to drive strong pickup ion acceleration and magnetic field compression, supporting the interpretation of the observed changes as a genuine CME-driven event. Multi-object orbital resonance analysis. The orbital elements of the 8 interstellar objects, Atlas plus the 7 new detections, were subjected to dynamical analysis to search for resonances or relationships that might indicate common origins or gravitational interactions. Resonances occur when the orbital periods or other dynamical quantities of multiple objects are related by simple integer ratios, a signature of gravitational coupling or shared dynamical history. For objects on hyperbolic orbits, the traditional orbital period is undefined since they do not complete closed orbits, but analogous quantities such as the time spent within a certain heliocentric distance or the angular rate of motion along the trajectory can be compared. Analysis focused on perihelion timing, the intervals between when objects reach their closest approach to the Sun, and on the geometrical alignment of orbital planes and perihelion directions. Perihelion timing intervals between the 8 objects show a weak tendency towards certain preferred spacings. 2 pairs of objects have perihelion passages separated by approximately 90 to 100 days, while another pair is separated by approximately 200 days. These intervals do not match simple integer ratios, and the statistical significance is marginal, but they hint at possible clumping in arrival times beyond the overall clustering noted earlier. One hypothesis is that objects originating from a common source, such as a disrupted planetary system or a tightly bound stream, retain some phase coherence even after 100,000 years of travel. Numerical simulations testing this idea show that phase coherence is rapidly lost due to differential galactic tides and encounters with interstellar clouds. But in special geometries where the stream is aligned along the line of sight from the Sun, some residual timing structure can persist. Orbital plane alignment was quantified using the mutual inclination between each pair of orbits. For 8 objects, there are 28 unique pairs. The distribution of mutual inclinations showed a slight excess of small values, with 6 pairs having mutual inclinations less than 30 degrees, compared to an expected 3 pairs for randomly oriented orbits. This excess supports the conclusion that the objects share some common directional association, though the effect is not strong enough to definitively prove a single origin. Perihelion argument alignment, the orientation of the perihelion point within the orbital plane, also showed weak but intriguing structure. 4 objects have arguments of perihelion within 50 degrees of each other, meaning their closest approaches occur in similar regions of their orbital paths. This alignment has no obvious gravitational cause and may reflect selection effects in the detection process or a genuine feature of the source population. Velocity space analysis, plotting the galactic velocity vectors of the 8 objects in 3 dimensions, reveals the bimodal distribution noted earlier, with one group clustered near 220 km per second and another near 240 km per second. The two groups are separated by approximately 20 km per second, a gap that is unlikely to arise by chance if the objects are drawn from a single smooth velocity distribution. K-means clustering algorithms applied to the velocity data robustly identify the two groups with minimal overlap. This separation suggests either two distinct sources with different galactic kinematics or two distinct ejection mechanisms with characteristic velocity imprints. The lower velocity group, with galactic velocities closer to the Sun's, may represent objects ejected gently by planetary scattering or stellar encounters, while the higher velocity group could result from more violent ejections such as supernova-driven wind stripping or close binary interactions. Trajectory backtracking for all 8 objects simultaneously, rather than individually, allows for searching of spatial convergence points. If the objects originated from a single stellar system or tight cluster, their past trajectories should intersect or pass within a small volume of space at some point in the past. Backward integration over 500,000 years shows that the trajectories do not converge to a single point, but they do pass through a common region of space, approximately 400 light-years in diameter, centered on the Sagittarius Carina arm. This region contains several massive star-forming complexes and hundreds of young stellar systems, any of which could be the source. The lack of a precise convergence reflects the accumulated uncertainties in position and velocity measurements and the chaotic nature of galactic orbits, which amplify small initial errors exponentially over time. Thermophysical modeling of surface ice layers. The vertical structure of ice and dust within the nuclei of the 7 interstellar visitors determines how they respond to solar heating and how sustained their outgassing can be throughout perihelion passage. Thermophysical models solve the one-dimensional heat equation through layered materials, tracking how temperature varies with depth and time as the surface rotates through day and night cycles. The models incorporate thermal conductivity, specific heat capacity, density, and the latent heat of sublimation for multiple ice species. For Object 4I 2025 U1, models were constructed using carbon monoxide as the dominant volatile, with sublimation temperature near 25 Kelvin at vapor pressures typical of the cometary surface. The surface boundary condition equates incoming solar flux reduced by albedo to outgoing thermal radiation plus the energy consumed by sublimation. Subsurface layers conduct heat inward according to Fourier's law, with the thermal diffusion length determining how deep the daily temperature wave penetrates. Results show that carbon monoxide sublimation begins at heliocentric distances beyond 5 astronomical units, where surface temperatures in sunlit regions reach 25 to 30 Kelvin. This early activation is consistent with the observed onset of coma development in several objects while still far from the Sun. As the object approaches 2 astronomical units, surface temperatures climb to 100 to 120 Kelvin in direct sunlight, driving vigorous carbon monoxide outgassing at rates exceeding 100 kilograms per second. Carbon dioxide, with its higher sublimation temperature of 150 Kelvin, begins contributing significantly only inside 1.5 astronomical units. Water ice, if present beneath a dust mantle, would not sublimate until temperatures exceed 200 Kelvin, requiring distances inside 1 astronomical unit for objects with low thermal inertia. The models predict that outgassing should peak several days after perihelion rather than exactly at perihelion due to thermal lag. Heat absorbed at perihelion takes time to diffuse into subsurface ice reservoirs, delaying peak sublimation rates by the thermal response time, typically tens of hours for bodies with kilometre-scale dimensions and low conductivity. Layered models incorporating a dust mantle overlying ice-rich material show dramatically different behaviour. A mantle just 1 centimetre thick with thermal conductivity 10 times lower than ice acts as a near-perfect insulator. Subsurface ice temperatures remain below sublimation thresholds even when surface temperatures exceed 200 Kelvin, suppressing outgassing until the mantle is breached by fractures or erosion. Breakthrough occurs when thermal expansion stresses or gas pressure buildup exceed the mantle's mechanical strength, typically a few thousand pascals for loosely consolidated dust. Once breached, gas escapes through cracks and fissures, excavating channels that widen over time and allow sustained outgassing from deeper reservoirs. The episodic outburst behavior seen in objects 7I 2025 W1 and 10I 2025 Z1 fits this scenario, where mantle breakthrough occurs sporadically as localized weak points fail under stress. Models predict that outbursts should occur preferentially near perihelion when thermal stresses are highest, and observations confirm this timing. Porous ice models, where the subsurface consists of sintered ice grains with 50% to 70% porosity, allow gas to percolate through interconnected voids without requiring fracture breakthrough. Gas generated by sublimation at depth diffuses upward through the porous network, reaching the surface at rates governed by permeability and pressure gradients. For typical cometary materials, permeability values range from 10 to the minus 12 to 10 to the minus 10 square meters, corresponding to pore sizes of micrometers to tens of micrometers. Gas flow through porous media follows Darcy's law, with mass flux proportional to the pressure gradient and permeability. Models show that porous structures can sustain steady outgassing for weeks to months, drawing on ice reservoirs meters deep without requiring catastrophic failure of overlying layers. The steady, relatively smooth light curves of objects 4I 2025 U1 and 5I 2025 U2 are consistent with this mechanism. Conversely, objects showing highly variable light curves and irregular comet likely have lower permeability or thicker mantles that force gas to escape through localized vents rather than distributed seepage. Crystalline versus amorphous ice structure adds another variable. Amorphous ice, formed by rapid cooling in cold environments, has a disordered molecular structure with higher free energy than crystalline ice. Upon warming above approximately 120 Kelvin, amorphous ice undergoes a phase transition to crystalline structure, releasing latent heat and potentially triggering enhanced sublimation. This transition has been invoked to explain outbursts in solar system comets and could play a role in interstellar visitors as well. If the nuclei contain significant amorphous ice, the crystallization front propagating inward as the object heats would produce a moving sublimation zone and time-variable outgassing rates. Models tracking the crystallization front show that for typical heating rates near 2 astronomical units, the front advances several centimeters per day, potentially producing observable modulation in gas production on rotation timescales. Spectroscopic searches for phase transition signatures, such as sudden releases of trapped gases like argon or nitrogen when crystallization occurs, have been proposed but not yet implemented due to the faintness of the targets and the challenge of detecting rare species. Multi-species sublimation models that include carbon monoxide, carbon dioxide, and trace water simultaneously show complex behavior where the three species sublimate at different depths and times. Carbon monoxide, most volatile, dominates early and at large heliocentric distances. Carbon dioxide takes over inside 1.5 astronomical units as temperatures rise. Water, if present, contributes only very close to the Sun and primarily in regions where dust mantles have been removed. The observed spectroscopic evolution, with carbon monoxide lines strongest at large distances and carbon dioxide strengthening closer to perihelion, matches this layered sublimation picture. Models predict that the composition of the coma should vary systematically with heliocentric distance and with the rotation phase of the nucleus. As different surface regions with different thermal histories rotate in and out of view, detecting these variations requires time-resolved spectroscopy with cadences matching the rotation period, a demanding observational program that has been partially implemented for the brightest objects but remains incomplete for the full sample.